And everybody can read that one? Maybe.
What's that? CT naught?
T naught, yeah, the inlet temperature.
Oh.
Remember that temperature might not be constant, right? So that's the, but that's the, for all of these, it's the inlet is what I'm writing up here. CA naught, YA naught, CT naught. Everybody see that? Of course you
Wait,
can
is
see
it C times T or is it C times little t?
total. This T's total,
Oh, no.
this T's temperature. The total concentration of gases. All right, so for a CSTR, yeah.
If we're using NOT for initial conditions, we refrain from using O to represent like the outflow outlet. Doesn't get very confusing.
I haven't used O to represent outflow. Yeah, you generally won't. I don't think it's in the book either. But yeah, I'll try to remember not to, but I don't think I have today. Yeah, and it's fine. I mean, you're not going to lose points on a test if you write FAN, like IN. I mean, I'm going to know what you mean. You don't have to use this nomenclature, as long as everything you're doing is, correct. I mean, don't, like, invent your own nomenclature. But a subscript or two can change. I don't want to see, like, a new language on some test from some smartass. All right, so this is for CSTR. This is the design equation again, now written in terms of, this is what we wrote before, right? In terms of flows. Often more convenient to write it in terms of conversion, okay? And now for a PFR, we can do the same thing. That's what we had in terms of flows. That was a design equation. Now again, if we want to write it in terms of conversion, that's what we get. So if we want to write it in terms of volume, like we did with the CSTR, that's the equation. So can we solve this analytically? Maybe, right? But we would first need to write out how does rate change as a function of conversion. Right? It's not like the CSTR where we can just pull it out because we know that it's constant. Why is the rate constant up here? So that we don't have an integral.
It's steady state.
Steady state, but a steady state for a PFR too.
You assume it's well mixed?
It's well mixed, right. The entire reactor volume is operating at the same conditions. That's not true for the PFR. That's the big difference between the two. And then the PBR, you guys might be able to guess, but you get so instead of solving for volume, now we're solving for what? Mass of catalyst. And what do those primes mean on the rate? Yeah, that's it. It just means that I'm writing the rate in terms of per gram of catalyst. So yeah, in order to solve any of these, well, to solve these later too, you have to know how does the reaction rate change with conversion, right? And in some sense here, that's true as well, because the reaction rate that you're using here is the reaction rate at a specific conversion. It's the outlet conditions. So now we're going to talk about something called Levenspiel plots. Okay, so RA depends on what? Temperature, concentration. For a single reaction, you can rewrite the rate as a function of conversion, okay? Still a function of temperature, but the temperature dependence, and this is true here as well, remember that's inside the rate constants. So let's look at an example. For a first order reaction consuming A, what's the reaction rate equation? K times the concentration of A. Pretty simple, right? Now how can I write that in terms of conversion?
Rewrite CA.
What is CA equal to in terms of conversion?
Something times volume. And then
Nothing times volume. So I don't know if we wrote this in terms of concentrations, but we definitely wrote it in terms of number of moles, right? So that's it. So then we just come back up here, K times CA naught.
Good.
Now, here there's something called the Levenspiel plot. Yeah. And on this plot, what you plot is -1 divided by RA. And on this axis, you put conversion. So 0 to 1, right? That much we got. Conversion is bounded. And the rate is just whatever the rate is. So what is -1 over RA for this reaction?
1 over KC, or KCA naught 1 over
Right? And you guys all know exactly what shape that makes, right? That's the shape, okay? So, I might have curved that up a little bit too fast. Should curve up a little bit closer to 1. So what happens as x approaches 1?
It goes on.
Yeah. This approaches infinity, right? Everybody see that? As the rate as conversion approaches 1 over the rate. Remember that the rate will approach 0 for a first order reaction. If you don't have any A, you can't do the reaction anymore. So 1 over the rate approaches infinity, this is for an irreversible reaction. Okay, and that's what we started with, so you guys weren't wrong when you said it approaches infinity. What do you think happens if you have a reversible reaction?
Approach equilibrium.
That's right. As 1 over as the rate approaches 0, in other words, the conversion doesn't approach 1, but it approaches some equilibrium value. But we wrote this as an irreversible reaction. That's why RA doesn't include any terms that say something like K minus 1, right? You guys remember those from the homework. Yeah.
So on a plot where you again have x runs from 0 to 1, you hit equilibrium, right? And then we have a negative rate afterwards, so we give a phase shift, a sign shift. Yeah.
It would look like that. The rate would be essentially the rate of the reverse reaction, the net rate of the reverse reaction would be 0 near equilibrium. Far away from equilibrium, the rate that you're drawing, yeah, you'd be underneath the axis. So you'd have this would be,
What is it?
this is, so for an irreversible reaction, this would just stop at 1. For an equilibrated reaction, it doesn't stop at 1, it stops at x equilibrium is where this hits infinity. Beyond that point, the rate is reversed, right? Instead of consuming A, in this case, you'd be producing A. Because you've gone too far. So now you're going to start producing A again to get back to equilibrium. Does that make sense to everybody? All right, so let's look at an example. For a CSTR. We're going to size a CSTR. So starting with the design equation, FAO times X divided by the rate of consumption at what point of a CSTR? The exit. Yeah. So if I give you, if you're given the rate of consumption as a function of x, right? I might ask you to find the volume needed to get to, let's say, 80% if FAO all right, so taking these equations, V So if I rearrange this, I can write the volume divided by the inlet feed is equal to whatever this consumption rate is at the conversion. Because remember that the exit condition is at that conversion, right? So at some specified conversion times that conversion is again equal to the volume divided by the inlet feed rate. So if we just put in numbers here, we won't put in numbers for that right now, but just these numbers. 0.8 is the conversion, not 80. Everybody get that? Okay, you don't put in the percent conversion, you put in the fractional conversion. And then, of course, that's just times 0.8. So let's look at if we do this on a plot, what conversion are we at? So there's our rate, and if you want the number for this example that's in the textbook, that's the number. Again, where did that come from? Not all your examples will just provide you with that, but this one does. It just provides you with the number. So this value over here is 800 with some crazy units. And so the volume that you get, you just rearrange this and you plug in that FA naught. All right, everybody see that? All I do is I just put this back over here. So it's the initial flow rate times this value, which is 1 over A, at that conversion, times the conversion, until you get a value of 555 decimeters cubed. If I had the plot, what could I do to get that area? Almost. But think about what I did. I multiplied 0.8 times that value. So it's not the area under the curve, but it's in fact this entire area, right? Everybody see that? This area is equal to the volume divided by the initial flow rate. So again, come back to here. Conversion times 1 over the consumption rate. That's what that plot has. Conversion times 1 over the consumption rate. So that area is simply equal to the volume divided by, in this case, the feed flow rate. And then, of course, if I give you the feed flow rate, you can get the volume. So if they give you a number for that inverse flow rate, or the inverse consumption rate, then your job is really easy. Just do it numerically. Sometimes, though, you're not going to get a number. You're going to get this plot. Okay? Does everybody see how to take this plot and get the exact same value? You just got to figure out, at your conversion, what is my inverse consumption rate? And that's the y-axis on that plot. All right, let's do a second example. Now we will do, I'll erase the numbers on here. We're still going to go to 80% conversion, so we'll leave some of this up here. But now we're going to do it for a PFR. So what's the design equation? Might have it in their notes. Let's do this one. Let's put it into terms of conversion, right? And then, of course, we could rearrange that and solve for the volume